Let's look at another example. You might ask, is economics scientific? Suppose you're an economist and you want to examine people's views of economics as an academic field. So you gather data on a random sample of Americans, and you want to test the claim that the proportion of respondents who think economics is a science is about the same as that for physics, with the alternative is that the proportion is less than that for physics. So this is sort of testing the claims by some scholars that maybe economics is not quite as scientific as it might seem. So we're going to look at the science data set. The sample size here is 1,756 US adults. Again, this is a real data set. This does reflect a real set of information about what Americans think about different scientific fields. Are they scientific or not? So we might say, what is the proportion of people who think physics is scientific? This will affect our null hypothesis for this particular problem. So the proportion in our sample who think physics is scientific is about 96%, right? So the sample proportion for physics is 0.96. The proportion who think economics is scientific is about 0.54. So our value of p hat is 0.54. Now for this particular setup, we're going to treat that value of 0.96 as our null, right? Because the null here is that the proportion of people who think economics is scientific is about the same as that for physics. So for the purposes of this problem, we're going to treat 0.96 as our null, right? The idea is that economics is just as scientific as physics, and we're going to test that claim using a value of 0.54 for p hat. So first we're going to check the success-failure condition as a preliminary step. So using p hat as an estimator for p, the idea is that we want to assess this assumption that n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10. So we can check the condition. The expected number of successes is about 948, and the expected number of failures is about 808. Both of these are much larger than 10. So we're pretty confident that the success-failure condition will hold for this particular problem, and accordingly, that sampling distribution for p hat can be approximated by a standard normal distribution model. Again, this is just reflecting the fact that with a larger sample size, we're more confident that that sampling distribution for that sample proportion will be approximately normal. So we're going to go ahead and proceed with a one-sample z-test. For steps 1 and 2, we want to set up our hypotheses and set our significance level alpha. We're going to conduct a left-sided test, so we have the following hypotheses, where the null proportion is 0.96. So the null is that economics is just as scientific in terms of its perception among the American public as physics. So the idea here is that the population proportion for economics is 0.96. 96% of people think economics is scientific. The alternative is that the proportion is less than 0.96. Now the way we've set up this problem, we're not really even considering the fact that maybe economics is considered more scientific than physics. We're not even considering that, because we're really interested in, is economics as scientific or is it less scientific in terms of its perception among the American public. We're going to set alpha to 0.05, so the critical value for this left-sided test is going to be negative 1.645. Then we calculate the z-test statistic. The z-test statistic is this sort of standardized difference between our sample proportion and our null proportion. The idea is the more extreme that z-test statistic, the more inconsistent our data is with that null hypothesis. So p hat is 0.54. That's our sample proportion for the percentage of Americans who think economics is scientific. The null is 0.96, and our sample size is 1,756. So based on this information, we can calculate a standard error of 0.005. That is our expected standard deviation of the sampling distribution for p hat. Then we can calculate a z-test statistic. The z-test statistic is negative 84. Keep in mind, at this point, you should know something about the standard normal distribution. Negative 84 is a very extreme test statistic, because we know, based on the normal coverage rule, that roughly 95% of all values we'd expect to be plus or minus 2 standard deviations within the mean. Well, negative 84, that's 84 standard deviations below that claimed value of that distribution, so of the null hypothesis. That's a very extreme test statistic. But formally, we can compare that test statistic to a critical value, and we can also calculate a p-value based on that test statistic. So we're conducting a left-sided test. The idea here is that we're interested in a z-test statistic less than negative z alpha divided by 2. And if that occurs, then we're going to reject the null. So in this case, negative z alpha is negative 1.645. So since negative 84 is much less than negative 1.645, negative 84 lies in that rejection region, we're going to reject the null that the population proportion is 0.96 at the alpha 0.05 level. We can also calculate a p-value. Right? For a left-sided test, the p-value is simply the probability of obtaining a z-test statistic less than or equal to the one we obtained. In this case, the p-value is very, very, very close to 0. So here we have a visualization. Right? Assuming the null is true, right, you can see that that's where the sampling distribution should be located, that little distribution on the far right. Well, in fact, our z-test statistic, right, is way, way below. And the probability of obtaining a z-test statistic even more extreme than the one we obtained is almost 0. So we reject the null at the alpha 0.05 level. Now we can make a conclusion. So we reject the null that the proportion of Americans who think economics is scientific is 0.96 against the alternative that the proportion is less than 0.96 at the alpha equals 0.05 level. So what we're going to conclude is that Americans do not think economics is as scientific as physics. Now, of course, we might say, well, maybe economics is as scientific as physics, but in terms of its perception among the American public, that is not the case. Americans view physics as much more scientific than economics. Of course, I always recommend to calculate a confidence interval. So the confidence interval is p hat plus or minus z alpha divided by 2 times the standard error. We're going to use p hat now as an estimate of p when we calculate the z interval. So we can conclude that we're 95% confident that the true population proportion lies in that interval. As another example, let's compare economics with accounting. So again, imagine you're an economist and you want to examine people's views of economics as an academic field. So we again have a random sample of US adults, but now you want to test the claim that the proportion of respondents who think economics is a science is about the same as the proportion for accounting. The alternative now is that the proportion is greater than that for accounting. So let's look at the science data set again. The sample size is 1,756 US adults. What is the proportion of people who think accounting is scientific? That proportion, in this particular instance, will be our null hypothesis. So the proportion who think accounting is scientific is 0.34. About 34% of people think accounting is scientific. Not that high, but it might reflect this idea that accounting is cooking the books. You can always say something using creative accounting. The proportion who think economics is scientific is, again, 0.54 or 54%. So thus we have a value for the null of 0.34, so p subscript 0 is 0.34, and our sample proportion is 0.54. Now we're going to check the success-failure condition before we begin hypothesis testing. Using p hat as an estimate for the population proportion p, we want to test the claim, or the assumption rather, that n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10. Both instances, for both successes and failures, the expected number of successes for this sample size is about 948, and the expected number of failures is 808. So in both instances, these are greater than 10, so we can proceed with a one-sample z-test. Because since the success-failure condition we'd expect to hold, that sampling distribution for p hat we expect to be approximately normal, and so we can use a standard normal model as to approximate that sampling distribution. For steps 1 and 2, we want to state our hypotheses and set our significance level alpha. In this particular case, we're conducting a right-sided z-test. So the null is that the population proportion equals 0.34, meaning economics is just as scientific as accounting. The alternative is that the population proportion is greater than 0.34. Economics is more scientific than accounting. We're going to set alpha to 0.05, so the critical value for this right-sided z-test is z alpha equals 1.645. For step 3, we want to calculate the test statistic. So the Z-test statistic for proportion is p hat minus p subscript 0 divided by the standard error. Again, all this is doing is it's calculating how inconsistent is our data, represented by p hat, from the null, represented by p subscript 0. And the more extreme that test statistic, the more inconsistent our data is with the null, and the more likely we are to reject that null. Since p hat is 0.54, the null proportion is 0.34, and n is 1,756, we can calculate the standard error. And that standard error is 0.011. That is just what we think the standard deviation of that sampling distribution to be. Right? Now we can calculate the Z-test statistic, which is that difference between p hat and the null proportion. And that Z-test statistic is 18.18. This Z-test statistic lies on the standard normal distribution. Since you should know the standard normal distribution by now, you should know that that's a pretty extreme test statistic. Just thinking about the normal coverage rule, we'd expect most of the values to be, 95% of those values to be plus or minus 2 standard deviations within the mean. In this case, 18.18, far out in an outlying region of this distribution. For step 4a, we can compare the test statistic with a critical value to really make a formal decision about a null. So we're conducting a right-sided test, so if our Z-test statistic is greater than Z alpha, we're going to reject the null, that the population proportion is 0.34. With an alpha of 0.05, the critical value is 1.645. That's the benchmark by which we compare our Z-test statistic. Since 18.18 is much greater than 1.645, we reject the null at the alpha 0.05 level. Besides comparing our Z-test statistic to a critical value, we can also calculate a probability or p-value using our Z-test statistic. For a right-sided test, where the alternative is that the population proportion is greater than the claimed value of the null, the p-value is the probability of obtaining a Z-test statistic greater than or equal to the one we actually obtained. In our case, this p-value is very, very close to 0. So you can see here, if the null is true, we have sort of a location of where we think the sampling distribution should be. That's if the null is true. And then you see that based on our data, we have the Z-test statistic. Our data lie really far in the extreme positive area of this distribution. And the probability of obtaining an even more extreme test statistic is almost 0. So in this case, we reject the null hypothesis at the alpha equals 0.05 level, because that probability value, that p-value, the probability of obtaining a test statistic as or more extreme than the one we actually obtained under the assumption that null is true, is almost 0. Now we can make a conclusion, either using what we learned about comparing our Z-test statistic to a critical value, or calculating a p-value using our test statistic. In either case, we reject the null that the proportion of Americans who think economics is scientific is 0.34 against the alternative that the proportion is greater than 0.34 at the alpha 0.05 level. Substantively, we conclude that Americans think economics is more scientific than accounting. So this kind of reflects the conventional wisdom that maybe accounting is cooking the books. However, again, this does not mean that economics is in fact more scientific than accounting. Maybe, in reality, maybe in just the way it's actually conducted, economics might be less scientific than accounting. Because what we're doing here is we're looking at perceptions of these different fields. According to perceptions, Americans think economics is more scientific than accounting. And of course, let's calculate a 95% confidence interval. We take our point estimate, p hat, plus or minus z alpha divided by 2, times the standard error. So the standard error, we're going to use p hat as an estimate for p when we calculate a z interval. So we can conclude that we're 95% confident that the true population proportion lies in that interval. A few things to know based on dealing with the one-sample z-test for a sample proportion. The one-sample z-test can be used for proportion given the success-failure condition holds. We don't actually know whether it holds unless we know the population proportion, but we can check it. We can assess how confident we are. In general, larger sample size suggests more confidence that that success-failure condition holds, and accordingly that we expect that sample proportion to be approximately normally distributed in terms of the sampling distribution. The main steps for testing a claim about a population proportion are identical to that for testing a claim about a population mean. This is where statistics is quite forgiving in the sense that the test for hypothesis testing pretty consistent. All right. Depending on the nature of the alternative hypothesis, we might have two-sided, left-sided, or right-sided tests. And with that, we've concluded our discussion of the one-sample z-test for a sample proportion.